Okay, so you have definitely seen this shape before. I mean, it's everywhere, from your old test scores to major scientific breakthroughs. It's the bell curve. But here's the thing, it's so much more than just a graph on a page. It's this incredible story about how pure, utter randomness can somehow lead to almost perfect predictability. So today, let's demystify it. All right, let's start this off with a bit of a puzzle. What could possibly connect the grades from your high school class, the heights of every single person living in a city, and, get this, the random, jittery movements of microscopic particles in a gas? I mean, on the surface, they seem completely unrelated, right? But there's a hidden pattern, a secret language that links them all. And the answer is, they all tend to follow the exact same mathematical pattern. It's called the Gaussian distribution. Now, you've probably heard it called the normal distribution, or even more simply, the bell curve. This shape, it turns out, is one of the absolute cornerstones of statistics and understanding our world. To really understand its power, we gotta start with the basics. So, let's break down the iconic bell curve itself and see what makes it tick. Now, I know what you're thinking. This formula looks a little intense. But trust me, the secret to that beautiful bell shape is hiding right there in plain sight. It's the e raised to the power of negative x squared. That little squared term is the magic ingredient. Why? Because it's squared. Plugging in a -2 gives you the exact same result as plugging in a +2. And that's what makes the curve so perfectly, beautifully symmetrical.
So every single bell curve you will ever see is defined by just two simple knobs that we can turn. The first one is the mean. You can just think of this as the center. It's the most likely outcome sitting right there at the very peak of the curve. And the second knob is the variance, which is all about the spread. It tells us how wide or narrow that curve is going to be.
And this slide just perfectly illustrates what that spread knob does. If the variance is low, it means most of your data points are all clustered super tightly around the average, and that gives you a tall, skinny bell curve. But if the variance is high, well, the data is scattered all over the place, far and wide, giving you a short, flat, wide curve. It's the same fundamental shape, just stretched or squished. Okay, so that's the bell curve in one dimension. Simple enough, but let's be real, the world isn't a single line. It's incredibly complex, it's multidimensional, so how does this simple shape help us model entire, messy systems? Well, we make a leap. While a single Gaussian variable is just a random point on a line, a Gaussian vector is a point in a high-dimensional space. Think about it like this. To describe a person, you could measure their height, their weight, and maybe their blood pressure. Each one is its own random variable. A Gaussian vector describes all three of them at once as a single point in a 3D space. And in the most basic case, knowing one tells you absolutely nothing about the others. Now, when we say independence, we mean something very, very specific. It means the probability of one variable being a certain value gives you zero information about the others. Knowing someone's height gives you no clues about what their test scores are, for instance. But of course, in the real world, things are often connected, which brings us to our next incredibly powerful tool. Okay, this is where things get really cool. We're about to introduce the tool that lets the humble bell curve model the beautifully complex and interconnected systems that we see all around us every day. Meet the covariance matrix. Seriously, you should think of this thing as the DNA or the blueprint for a whole multi-dimensional system. It's this grid of numbers that doesn't just describe the spread of each individual piece, it spells out the entire rule book for how they all relate to each other. Let's just look at a simple 2x2 example. The numbers on the diagonal, those are the individual variances we've already talked about. Easy enough. But the magic, the real story, is in the off-diagonal numbers. These are the covariances. They tell us how the variables tend to move together. For instance, we know height and weight are positively correlated. As one goes up, the other tends to go up too. That relationship is captured right there in that number. And this reveals a unique superpower that only Gaussian distributions have. For most other types of data, just because two things are uncorrelated doesn't automatically mean they're truly independent. But for Gaussians, it does. If their covariance is 0, you can bet they are 100% independent. And let me tell you, that is a super useful property that makes statistical modeling so much simpler. So we have this amazing tool for modeling complex interconnected systems. But here's the twist, the truly counterintuitive part. When you put millions of these random Gaussian parts together into one big system, something amazing happens. They become incredibly predictable. This wild phenomenon is called Gaussian concentration. And the best way to wrap your head around it is to think about Earth's atmosphere. I mean, the atmosphere technically stretches for hundreds of kilometers out into space, right? But almost all of the air, all the probability, you could say, is concentrated in a very, very thin layer right near the surface. The exact same thing happens with these high-dimensional Gaussian vectors. They're overwhelmingly likely to be found in a very thin shell right around their average value.
And here's the part that just blows my mind. This concentration effect, this focusing of probability, it doesn't get weaker as you add more and more variables. The probability squeezes into that thin shell at the same rate, whether you're modeling 3 variables or 3 times million. This is what makes the math so powerful and scalable for massive, complex systems.
So what's the bottom line here? It means that even if every single component of a giant system is behaving randomly, their collective behavior can be almost deterministic. It's the reason we can make such stunningly accurate predictions about systems with millions of moving parts, from the pressure of Gauss in a container to the movements of the stock market. And this brings us right back around to where we started. We've seen how Gaussians work, how we can build complex models with them. But we still haven't really answered that first question. Why? Why is this one specific shape, the bell curve, so unbelievably common in the real world? The answer is one of the most beautiful and, I think, profound ideas in all of mathematics. It's called the central limit theorem. And you can basically think of it as the universal law governing large-scale randomness. Okay, let's just walk through it. The theorem says you can start with almost any kind of random data. It doesn't have to be bell-shaped at all. It could be totally flat, like rolling a die, or some other completely bizarre shape. You just take a bunch of samples from it, and you calculate their average. Then you do it again, and again, and again, thousands of times. And when you're done, you plot a histogram of all those averages you calculated. And what shape do you see? You get a bell curve. Every single time. It's like magic. It's an emergent property of the system. The sum or average of many independent random things, no matter where they started, will always converge to look like a Gaussian distribution. So why is this such a big deal? Because it shows us that there's a deep, hidden order within the chaos of randomness. It's the reason why things like human height, which is the result of countless tiny genetic and environmental factors all added together, falls into a perfect bell curve. This theorem lets us model incredibly complex systems with a ton of confidence, and that makes the Gaussian distribution arguably the most important one in all of science. So I'll leave you with this final thought to chew on. If the sum of countless, seemingly random events is so predictable that it follows a perfect mathematical law, well, what does that really say about the nature of randomness itself? Maybe our world is a whole lot more orderly than it looks on the surface. Thanks for joining me on this explainer.